All right. Shh. Okay, so first things first, systems. You guys did a lot with systems back in Math 1, but it was only linear systems. So now we're doing a combination of linear quadratic systems, which means it's a system including a quadratic equation and a linear equation. All right, it's pretty much about the same. Now, sometimes with quadratics, you may be given either a parabola or an equation of a circle. We'll talk about that in just a minute. Now, solving a system, more often than not, it means finding the points of intersection of the two relationships. So, first off, if we look at this first one, all right, first we're going to find the intersections of the curve algebraically. So think back to Math 1. What were the 3 different ways that you could solve a system? Say it again. So elimination, substitution, and what's the other one? What's the easiest way? So they said points of intersection. So what do you think that means? If you see points of intersection, that means you're looking at a what?
I thought this is what it is, man. Wait, that's equal to each other, right?
That's substitution. Graphing, guys. Solving by graphing. Points of intersection. Good God. Good God. Graphing's the easy one. All right, so hush. That's strike 1. Strike 3, I'm doubling your delta math. All right, so if we're going to solve it algebraically, do you see how both of these are set equal to y? All right, we can use substitution. Basically means since they're both equal to y, we can set them equal to each other. So I have 3x squared minus 8x plus 5 is equal to 4x plus 5. So doesn't this look like basically just a normal quadratic problem? Yeah, so how do I solve? Get it all to one side. That goes away. I get 3x squared minus 12x is equal to 0. Has a GCF factor, so 3x and then x minus 4 equal to 0. So if I set both of these equal to 0, x equals 0 and x equals 4. Now, we're not done because a system usually has what type of values? The solutions to a system is not just an x value, it's what? X and y values. So you have to take both of your x values that you got and plug them back into one of the functions. It doesn't matter which one, you should get the same thing. I recommend the easier one.
The 0.
No, I recommend plugging it into the easier function, so the linear one. So y is equal to 4 times 0 plus 5, so y is equal to 5 when x is equal to 0. Y is equal to 4 times 4 plus 5, so that's 16 plus 5, so y is equal to 21. So the system xy is equal to the set of the points 0, 5 and 4, 21. Those are the answers to our system. So in other words, if we were to graph this, those would be our 2 points of intersection. All right, so let's try graphing these. So What would my vertex be here? Or easier, what's some roots? What's my roots for the quadratic? 0, 0, and 4. So here and here. How can I find my vertex? Or at the very least, the axis of symmetry. So the axis of symmetry will probably be right here. That's halfway between 0 and 4, so at x equals 2. So that means vertex has to be at 2 for x. So if I plug 2 back in, no, because it's not the point of intersection. So it won't be equal. So 2 squared is 4. Hush. 2 squared is 4 times 3, that's 12. Minus 8 times 4, which is 32. So that's negative 20. Plus 5 is negative 15. So it goes off the grid a little bit. So that'll be like down here. Now,
Wait, isn't it 8 times 2?
yeah, I did it wrong. So that's 6 minus 16. So that's negative 10 plus 5. That's negative 5. It's right here. All right. Now, mm-hmm.
Can we like plug it into the other one then? Like
You cannot.
yeah, what's the easiest one?
That's only with the solutions to the system. Oh crap! So I lied. Okay, so we have to use the original. This is when we solved using the system. So if I find, so that's 15, so that's negative 5 and 3, so that would be, so if you factor this real quick, all right, if you do a quick factor on that, that would be negative 3, negative 5, so that would be 3x minus 5 and x minus 1. So the zeros are at 1 and 5/3, so that's slightly more than 1. All right, so let's just say the vertex is down here because that doesn't really matter. Now, we know our points of intersection are going to be here, and it's going to be here. So if I draw a generalized shape, because it doesn't have to be exact, I just want to draw a general shape. Now, 4x plus 5. What is it? How do I graph a linear? Well, no, duh, but how do I graph a linear function? That's basically all math 1. Right, it's rise over, hush. It's rise over run. Where do I start? At the y-intercept, which is 5. So that's why the intersection's there. Now, if I go up 4, so up 4 over 1, so that'll be here, up 4 over 1. Ugh, it's not going to be pretty. But let's just say, crap. So essentially, it'll end up being here. So this will be kind of what the graph looks like. Some quadratic crossing with a linear graph. And these would be your points of intersection. Now, the other way is to just put it in Desmos. So if I have Desmos open, if you graph both of them separately, so 4x plus 5 and 3x squared minus 8x plus 5, All right. It graphs both. Do you see how it already marks the points of intersection for you? You just have to click on them. You got the same thing that we solved algebraically. Yes.
Like on a test, would we be able to use it? So we have to do it.
You'll be asked to do it algebraically. So it's just showing where it is like that. Now, if you do get a quiz on this, you'll be able to use Desmos for like the word problems, but not for the systems because they can still be solved algebraically, but they'll be like easy systems.
But when you inbox, that is our answer.
Yeah.
So we don't have to graph it.
No, it's mostly just showing you what it looks like. Yeah, that was just a check to make sure that we were correct. You know what I mean?
And then, so the other, the y equals 3x squared minus 8x plus 5.
We're about to do that.
You said that.
Oh, say it one more time.
Like, why did you do that? Was that for the line? Or
So y equals 3x squared minus 8x plus 5, that's this curve right here. So the parabola. The line is 4x plus 5. So this is 4x plus 5. This is 3x squared minus 8x plus 5. So essentially we graphed these two equations, found their points of intersection. All right, so let's do the same thing to solve this system. So they're both equal to y, so that means we can just set them equal to each other. So I have x squared plus 4x minus 15 is equal to 8x minus 3. So what do I do to solve first? Subtract the 8x and add the 3. That goes away. X squared minus 4x minus 12 is equal to 0. So what are two factors of negative 12 that'll add to 4? Negative 6 and 2. This will be x minus 6. X plus 2 is equal to 0. Thus, if we solve those equations, the x values are at 6 and negative 2. Now remember, those are our x values. We always have to find the y's. So we got to plug each x value individually into one of the original equations. Again, I always recommend the easier one, which more often than not, that's the linear. All right. So I'm going to plug in negative 2 in first. So if I plug in negative 2, that is 8 times negative 2 plus 3. So that's negative 16 plus 3. So y is negative 13. Oh my gosh. Yeah, negative 19. All right, I'm going to do the same thing for 6. I'm going to plug it in. So I have 8 times 6 minus 3, so that's 48 minus 3. So y is equal to 45. So then if I combine them, my set, xy, will be the solution set of negative 2, negative 19, and 6, 45.
do we go in order of like?
You don't have to. As long as the points are written correctly, so obviously put the x value before the y value, that's fine.
So we don't have to put like the lower x. Like,
No, I just kind of default to that. Any questions on how you solve a system of equations? Yes. Yeah. Now, there's also a system of inequalities. Now, the system of inequalities, I would 100% put in your calculator. All right. And this would not be on the quiz, but it's still good to see. So remember, the solution set of a system of inequalities is where the shading overlaps. All right. So you can literally plug these in verbatim into Desmos, and it'll do the shading and everything for you. So I'm going to do that. So in Desmos, I'm going to type in, and make sure you type in the y. Y is, what was it, less than or equal to? Wait, is it less than or greater than?
less.
No, that's definitely greater than.
Oh yeah.
What was it? Negative 2/3?
Negative 2/3 plus 8.
Thirds. Crap.
How do we do less than or greater? Or less than
You have to go to like the keyboard on the screen in Desmos.
or greater than?
The other one was less. Y is greater than or equal to what? X squared.
Minus 10 plus 23.
All right, so we're going to do kind of a quick sketch of what's going on. So I'm just going to get some points, random points. Okay. Huh? We're not solving this algebraically, not the inequalities. You could. I don't recommend it. So, vertex for this one is at negative 5, 2. Or 5, negative 2. And then, crap, y-intercept. Zero 23. All right, so here is, again, it's not going to be perfect. I'm just getting a couple of points. I just got the vertex, so at least it was in the right place. All right, now where did they shade? Did they shade on the outside of the parabola or inside the parabola? Inside. Now also, why is the parabola a solid line? Because it has the equal to, right? So if I graph this one, I go up to 8. I'm going down to over 3. So down to 3, and then so on and so forth. So pretty much this would be what it looks like. Now, did it shave above or below it? Above the line, so like this. So your answer is where the shading intersects. All right. Now, specifically, you're going to look for the points of intersection, which I did not graph this perfectly, so it's not going to be perfect. But your points of intersection are essentially your boundary. All right. So if I go back to Desmos, I want to click on these points of intersection, and they are ugly. All right. But we're still going to round. So these points will intersect at x equals 2.06, y equals 6.62. So our points of intersection are 2.06 and then 6.42? 62. And then this one was at, what's the other one at? And 3.15. All right. So now we're basically going to be discussing whether it's less than those numbers, greater than those numbers, or in between them. Okay. So in terms of x values, all right, the x values, does it have to be between the x values or greater than or in between? So for the x values, we can say it has to be between 2.06, which is less than or equal to x, which is less than or equal to 7.27. Now, the reason I'm using equal to is because since one of these is solid, it overrides the non-equal to one. All right. The y's. Is it going to be between them, greater? What do you think? So look specifically at the y's.
In between.
It's in between, but it's also greater than them. All right.
Would it only be equal to the intersection?
So the y values have to be kind of between. So if you notice the y values, they don't get any, they kind of stop. So it's kind of between these two y values. But if you look up, the solution set keeps on going on forever up top. So in reality, the y's can kind of go to infinity. In reality, when it comes to solving the system, I just want the points of intersection and specifically where the x's will be. Yes.
Wait, but would the y's be equal to or
So another way you could state it, let's do this. Another way you could state it is the point xy. It has to be between these. Now I remember how to state it. This is how you state it. You basically do both points that it's between. And you base it based off of the x's, so from least to greatest x's. Now, again, we're not going to do systems of inequalities. I just wanted to show you what it would look like. But in reality, I would just want you to be able to identify where the intersection was.
Sounds like the answer that we have to write down.
Pretty much, yeah, this. All right, so we're not going to do exercise 4 because, again, I'm not going to really make you guys do inequalities. I just wanted to show you what it looks like. I'm more worried about the system of equations. Well, there's not really going to be a test for this. There may be like a short quiz, but that's, yeah. This isn't a test unit. All right, now here's the other one. Circles. All right. You'll do a lot more of this in Math 3, but you can also make these into systems. So equations of circles. Typically, it's a circle and a line. Now, just so you're aware, this is the typical equation of a circle, where this is the x value, which we call h. This is the k value of your center point, and this is your radius squared. So this is a circle equation. The other one's just a regular linear equation. Now, to graph this circle, all right, so to graph this circle, what would the center be at? Do I have anything being added or subtracted to the x and y?
no? It should be 0.
So it'd be 0, 0. So the center would be 0, 0. Now, if r squared, so it's our radius squared, so what's our actual radius? So 25 is equal to r squared. So what's the actual radius? 5. So how we graph this circle is that basically I just go in all cardinal directions, meaning north, south, east, west. So I go 5 out in all directions. And my center's here. And then you just kind of sketch it as best you can. It's not the prettiest circle I've ever done, but it'll do. Yeah. So you just got to make sure that it goes through all 4 radii points. The center, it's not going to go through the center. Now, we're going to solve the system graphically by plotting the line. So this linear function, all right, so x plus 1, so where do I start graphing it? 0, 1. Then I just go up 1 over 1 for a while. Going to do the same thing on the other end. right. So my graph will look something like this. Now, again, it's going to be hard to see like when you graph it by hand because, drawing the circle isn't perfect. So let's double check where it's going to be in Desmos. So I have x squared plus y squared is equal to 25. And then I have y equals x plus 1. Oops. Now you may have to zoom out a little bit or zoom in. So Desmos will in fact graph circles for you. All right. Now, the points of intersection are here and here. So what are the 2 points of intersection? 3, 4, negative 4, negative 3, which, nope, I was way off with my drawing of the circle. All right. So let's imagine that this is the point 3, 4. And let's imagine that this is the point negative 4, negative 3. All right. So that's why typically if you have to solve graphically, I recommend using a graphing calculator of some shape or form just to get it exact, because a lot of times drawing it by hand, it's not pretty. So those are our points of intersection. So that's what xy is equal to. Now, let's say we wanted to solve this algebraically. We would have to use substitution. So what does that mean?
Y equals set x or y on one side and replace x or y.
Right. So if we look, y is already by itself for the linear function. So all we really have to do is take this x plus 1 and plug it in for this y. So I have x squared plus x plus 1 all squared is equal to 25. So I have x squared. If I expand x plus 1 squared, what is it?
X squared plus 2x.
Good. It's a perfect square trinomial. So it's not x squared plus 1. You got to have that 2x in there equals 25. Do some simplifying. I get 2x squared plus 2x plus 1 is equal to 25. Subtract the 25 over to get one side equal to 0. 2x squared plus 2x minus 24 is equal to 0. Right. I can start by factoring out a 2. So I have x squared plus x minus 12 is equal to 0. Now, since we're solving, this 2 just kind of doesn't matter anymore because you'd end up dividing it out anyway. How would I factor x squared plus x minus 12? X plus 4, x minus 3 equals 0. So the x's is equal to negative 4 and positive 3. If we plug it back into one of the functions, again, pick the easier one. I'm going to pick the one where we only have to add 1 to the ones. So I have negative 4 plus 1, which is negative 3. So that's equal to y for negative 4. And I have 3 plus 1, which is 4, which that's the y value. So we still get the exact same thing. xy is equal to the set of negative 4, negative 3, and 3, 4. Now, that was if our circle is centered at the origin, but that's not always the case. All right. Sometimes it's not. So let's look at this last one. So we're still going to use substitution to solve this algebraically, but now this 3x plus 10 is going in for this y, so we're going to have to do some simplification in the parentheses and then square it and all that stuff. Yes? Okay. So I got x plus 2 squared plus 3x plus 10 minus 4 all squared is equal to 40. PEMDAS says I can simplify in parentheses first. So I have x plus 2 squared plus 3x plus 6 squared is equal to 40. So if I simplify both of these, this will be x squared plus 4x plus 4 plus 9x squared plus 36x plus 36. And it's all equal to 40. And again, I just did that because it's perfect square trinomials and I know the rule for it. We talked about that in the last unit. You could always do a box method if you need to. I'm just doing this quick because that's something that I don't need to go over with you guys. All right. I'm more worried about can you solve. So what do I do next from here? Combine the like terms. So I have 10x squared. What's my x's? Plus 40x plus 40 is equal to 40. Now what do I do? Subtract the 40 from both sides. That's gone. I have 10x squared plus 40x is equal to 0. Now I can do a GCF. What? Bigger 10x, at least with x plus 4, is equal to 0. Set both of them equal to 0. X is going to equal 0 and negative 4. Now, I'm going to plug them back into one of the functions. Again, I pick the one that's easier. So if I do 3 times 0 plus 10, y would be equal to 10. If I do 3 times negative 4 plus 10, that's negative 12 plus 10, so that's negative 2. Put everything together. My set is xy is equal to the set of negative 4, negative 2, and 0, 10. Any questions on those? How you guys feeling about systems? I don't really care about the inequality systems, but how you feel about systems of equations? Not bad. It's okay. As long as you've seen it before. Basically, most of this is just going to be plugging stuff in for y or setting them equal to each other and solving a quadratic. Any questions? Any questions? Speak now, forever hold your peace. All right. Okay. Okay. Shh. Moving on. Modeling. Now, we did some of this back in Unit 3. All right. So, if an object is fired upwards with an initial velocity of 112 feet per second, the height above the ground is a function of time, which is this function. So, what is the height that the object was fired? 0. There's no constant, so it's 0. So 0 feet. Because remember, it's based off of your C value. Do we have a C value?
Yes.
Well, we technically do, but it is 0. Now, if we sketch a graph of what's happening, all right, it looks something like this. It's launched here. It goes up, 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 comes back down, and hits somewhere here. We don't know where that is yet. Now, find the time that the rocket reaches its greatest height algebraically and the maximum height. So think about this. Essentially, we're looking for the what on the graph? The vertex. So how do I calculate the vertex algebraically using the standard form? It's what? There's a formula. You could do vertex form, but I don't want to complete the square. It's too much work.
Oh, negative b.
There you go. Negative b over 2a. Because remember, negative b over 2a calculates the axis of symmetry, which is the x value of the vertex. To get the y value, you just got to plug it back in. So I have negative 112 over 2 times negative 16. So that's negative 112 over negative 32, which is what?
4.
You guys have calculators, use them.
3.5.
3.5. So in other words, it reached its highest height at 3.5 seconds. So that's the first part. Now it wants us to find the actual maximum height. So I'm going to plug this 3.5 back into the original equation. So I have negative 16 times 3.5 squared plus 112 times 3.5. Plug that into your calculator carefully and tell me what you get. It's 96. 196. Did everyone else get 196? All right, so 196 what? Feet. So if we go back to our sketch, this point right here will be 3.5 and 196. Now, algebraically, we're going to determine the time when the rocket reaches the ground. Technically, but not always. It depends on the actual velocity. So, and it also depends on where the initial height is. Yeah. All right, so, but algebraically, you just factor. So if we solve this, all right, this one's easy because reaches the ground, what are we looking for graphically? The roots, specifically the positive. So in other words, we already know how to do that algebraically. What is that essentially? Solving by factoring. So I'm going to set negative 16 t squared plus 112 t equal to 0. All right. Don't I have a GCF? It's negative what?
Yeah, negative 8t.
Negative 8t. So that leaves me with 2t minus what?
7. I don't know.
You have this thing called a calculator. Use it.
Of which it's not that much.
All right. There's actually a bigger GCF. That would be 16.
Oh,
That would be 7.
Yeah, that would be 7.
see, I was right. I just 2 steps ahead.
Okay.
All right. Then we would set both equal to 0. So t is equal to 0 and t minus 7 is equal to 0. So if I solve t is equal to 7. Now, which one am I using? That's the better question.
7.
Right. 0 would be over here, which that's where we launched from. That's not what I want. I want what it is after we hit the ground. So my answer is 7 seconds. All right. Now, some of these, it's more so a matter of just kind of figuring it out. All right. Some of these we're not going to actually do by hand because, like, it's just really hard to do by hand. So let's look at this next one. A projectile has a height given by this function. A drone, so this is a projectile, this is a drone, has a height given by this function. And its heights are in feet. Determine the 2 times to the nearest hundredth of a second when the projectile and the drone are at the same height. So this would be a what? It's a system. So if I drew a graph of this, all right, this would be the projectile. What's going on with that? Shh. All right. And this would be the drone. So it's not quite accurate, but it's pretty close. Now, if we wanted to attempt solving this by hand, how would we kind of set it up? So we would set them equal to each other. Now, we're not going to solve by hand because unless we're solving by factoring, we could solve by quadratic formula if we want to. I don't want to. So we're going to go to good old Desmos. But they're both functions of time, so it doesn't matter. So, and remember, GT and FT are just fancy names for Y. So, I'm going to type these in. So I have negative 16.1 x squared plus what was it? 120 what? It doesn't matter. And then the other one was 8.5x plus 85. So you might have to zoom out a little bit, or a lot. So they intersect here and here. So they're not going to be perfect. So this is why I said we didn't want to use, solve by hand, because it's not pretty. So at what times, let's say to the nearest 10th, because that's what it asked for, do they cross paths? Don't we have the points? So time, what value of the point is time?
0.89.
X. So 0.8. So 0.9 if we round. And what's the other one? 6.1. Because it wants it wants it in the nearest hundredth. So T would equal 0.87 and 6.05. So it would be at 0.87 seconds and what did I say? 6.05 seconds. So that's when they would be at the exact same height, which would be here and here. All right. I think we're going to call it a day. Okay, so
Can you just make the document tomorrow, like, available now, and then we can say, like, that works working on our
What do you want to have
so I was going to give you the paper assignment in here, but I don't really want to. I'll just go ahead and open your Delta Math so at least you can start working on that. Huh? The what? Oh, I went around and checked. Just bring it to me because you were in the bathroom, I think. Second place. Who's first?
What was it? 8, 9?
Yeah. All right, write the grade down.